Thank you very much. Lovely to see so many people. I cannot see everybody because I'm pretty much blinded, but that's okay. I know what I'm going to say, and I hope you are going to enjoy it. So, anyways, my name is Michael, obviously, and I'm from Systematic in Denmark. Is this one too loud? Is it okay for everybody? All right. We also have a little office down here at the Landmark where I've been many times. I'm teaching down there 14 days a year, so I enjoy that very much. And of course, that's about software security. So who am I? Or who are Systematic in general? Well, we make business and mission critical software. And the thing that's important in that respect is that we care a lot about quality. And 10 years ago, I was one of the people that made sure that quality also included security. So I've had a big chance in Systematic in relation to kind of tailor my own job description, because I started a lot of different kinds of initiatives because my interest in security kind of flourished back then. And so I started also studying security. I came into it just by coincidence, getting some tasks that were about security. And then I started studying software security as the first course. And then eventually, supported by Systematic, I got a complete master in cybersecurity. So, but software security, that is where my heart really lies. So, today, of course, it is also going to be about AI. So, well, what am I actually doing in Systematic, and why am I here today? Well, I started making a course in software security, where we are teaching our developers how to build security into the software. One thing that is very important in relation to software security. Then I wrote our secure development process, and which I'm still maintaining, and I started a red team. We probably ought to be called a purple team, because we are both doing blue team work, which is generally perceived as the proactive things we do in order to get good security, and then we are doing offensive security as a penetration testing team as well. So I use most of my time on all these things, and I enjoy it a lot. So, but let's get to the agenda today. And it's kind of short, but I also only have 40 minutes, and I'm known to talk a lot and talk for a long time. So I have really tried and restrained myself here. So, but first, we need to define what is actually software security, so we know why it is important in the era of AI. And then I have done some rethinking in relation to AI and security. And then I'll show you my 7 principles in the AI era here. Building security in, well, these are kind of dinosaur books from Gary McGraw. This is one of the ones I read. And he's defining software security in contrary to what we call application security. Application security is the thing that we have been doing for the past 30 years. We are building a system, we are doing everything as we know, and then in the end, we are putting it into a secure box made of firewalls, intrusion detection systems, intrusion protection systems, and SIEM, and SOAR, and all those kind of tooling things we can do. But we need to make software that is strong from within. So like this piece of wheat coming up through the paveway, we need to be strong from within. What does that require? Well, in general, McGraw says that software security needs to, in order to be successful, to build on 3 different pillars. The one is risk management. You simply need to know what are the risks in which we are deploying a system today. Secondly, knowledge. We need to get people aboard. We cannot any longer just stick to having 10 people sitting in the corner of the organization and making a lot of application security tooling in order to make our system safe. So we need everybody to know about security. Otherwise, how could they be able to build security in while they're developing? So that is where they really differ. application security as the reactive thing, the things we do afterwards, and software security like the things that we are doing upfront and during the entire thing. That brings us to the middle pillar that is called touch points. And that is because that is different things you can do to the ordinary software development lifecycle in order to make it secure and hence obtain a secure development lifecycle. So that is the thing I also wrote in Systematic. We're building on McGraw's things, and then we did a lot of extra things as well. So the fundamentals still hold, but gravity shifted. Imagine that you just built a great house. That house you built of the best of materials, the best floors, the best ceilings, the best walls, whatever you could think. Great house. Then you decide to hire, or at least purchase probably, maybe Ellen will sell you one, an autonomous butler. That butler you task with, you need to clean my house. Just keep it clean. And then this butler goes around in the house and he figures, all right, now I just see this great industrial vacuum cleaner on the internet, so I think I'm going to buy that one. I already can access the credit card details and so I'll buy this vacuum cleaner. But it seems it's too big to fit into the doorway. So now the butler tears down the load-bearing walls and pulls in that vacuum cleaner. You could say kind of ruining the structural integrity of our great house. Well, we need to do something. The ordinary principles look like this from McGraw. Some of those are still part of the new list that we have. Some are going to go away. For instance, securing the weakest link, defense in depth, fail securely, keep it simple, hiding a secret is hard, and using your community resources. Well, they are all great principles. They still hold. But again, gravity shifted. Maybe we need to rethink. Maybe there are new things that are important in the era of AI. So, how do we think about security when everything is changing? Maybe we can pull this quote out. Some of you that might be as old as me will definitely recognize it from the 1999 Matrix serial from Agent Smith. There's no escaping reason, there's no denying purpose. The point is, if you have an AI agent in a system, a relentless optimization machine, it will do whatever it can to fulfill its purpose. You need to design the limits in your system because it will try to express its purpose whether or not your security architecture actually is ready for it. So the system changed. Now, you used to be a programmer. Now you're going to be an AI pilot, and we are going to navigate systems of unbounded complexity. There are so many so-called attack vectors, more about those later, that has happened. It might look friendly at first, but there are so many holes in this system that we need to kind of navigate. For that reason, there are new principles lined up. More about them later, but they are threat modeling, being reluctant to trust, good old one, minimizing the attack surface, and compartmentalization. So 2 new and 2 from the old list. At the same time, AI changed the game. You are not coding alone anymore. Now you have a partner in crime. You got a co-pilot. He so happens to be a mathematical genius, having complete encyclopedia knowledge. At the same time, it's incredibly gullible and will take any input it can if you can trick it. And it's not that hard to trick. So, principles. The first one, principle of least privilege. Promoting privacy and human in the loop. Now we're ready. These are the 7 principles. So let's look at what it really means. The total list is like this, and it is architected this way also. Some of the things that are important in order to get on this list is that for you as developers or parts of a development organization, these principles are some that you can actually fulfill in your organization. They are directly operational. And we'll get to what operations really are now. So, performing threat modeling. I have tried to make it operationalized in a way so we have some kind of oath standards. And the first oath is, I will never assume I fully understand how my system can be attacked and exploited without doing proper threat modeling. Now the question is, what the hell is threat modeling? Well, some of you might already have recognized that this one is the thing that fits the first pillar of software security, risk management. Threat modeling is generally just risk management about security. However, it's very important it's going to be done in a structured way. So just a little example here. Sorry for blinding you now. They will get back to blue in a minute. But here you see a general system. So we have a front end, a back end, and then we have something that comes from the outside. Now we are plugging AI into this system. We are having an agent sitting on the front end that can kind of serve a prompt and interact with our back end model. Then we have some RAG, private data stores over here to the right, retrieval augmented generation. So these are kind of the stores where we are uploading our proprietary documents that make sense in our domain in order for the model to make more sense in our domain. Then we have some vector databases, and everything is stored as vectors. So mathematical vectors in a geometrical space ranging from 384 to 3072 dimensions. And then in this big space, whatever is close to each other is very likely to be put out if it gets something in that is close to that. That is how it works. I know that was a very simple explanation. Threat modeling. What is that? Well, generally, you can follow Adam Shostak's 4-question framework. The first thing is, what are you doing? Basically, what kind of system is it that we are trying to build here? So far, we have nothing to do with security. You might make a diagrammatic overview of this system so you can also have it on a whiteboard. Number 2, what can go wrong? Now we start to look at security. So what are all the bad things that could happen just by looking at this diagram and looking at what kind of threats could hit us here? Number 3, what are we going to do about it? So now we're talking about the different kinds of risk responses. So can we mitigate? Do we have a plan B, a contingency plan? Maybe we can transfer some risk to people or organizations that better can handle them, as for instance our operations providers. Or maybe we need to accept something. In other words, we need to figure out what is our risk appetite. And then the final thing in Adam Shostak's lineup is, did we do a good job? So retrospective. So how well did we do threat modeling here? So in order to this concrete case here, the first thing we would do was to define a trust boundary. What is it actually that we think that we can trust in this system? Or in other words, what can we definitely not trust? So everything that is outside our circle of trust here is something we definitely cannot trust. a prime candidate to figure out where do we get the untrusted input. And that brings us to the next thing, which is so-called attack vectors. An attack vector is any place in the system. And here we need to remember or know that the system is everything. It is not only the software that we made, but also things that we are connected to or users that are using them. After all, humans are the weakest link, generally. So in our case here, of course, we have the prompt where we take direct input that is going to interact with our model. That's definitely an attack vector. Then we have a front-end API, we have an API endpoint, we have an ML engineer and a data scientist. Everything can be the source of untrusted input. Now, you can also see that there's something with the LM agents up here that are kind of on a red background. That is to indicate that, okay, apparently we have chosen to deliberately extend trust to these components. But are they trustworthy? Time will have to show. But generally, we probably should not just say, okay, we trusted them, so now everything is good. They also have attack vectors, because input and output still leave and come into these components. So with that, then we are able to figure out or kind of take different perspectives as to what kind of risks are in this system. Well, now this talk is not about threat modeling because 40 minutes and all that. But now at least you have a good idea of what it is. So it brings us to the next principle, being reluctant to trust. The oath is, I will always treat an AI system as an untrusted entity by being skeptic towards its output and treat it as an entity that can be swayed into malicious activity. Why I must validate and keep an eye on it. We are having a lot of different secure design and coding practices when we develop software in systematic. And trust is pretty much associated to everything. If you could just trust each other in this world, there would not be a big need for security. Of course, that would be bad for me, but anyways, now it's not the way it is. But the thing is, you need to be reluctant to trust. We're not saying trust no one, because usually we cannot build systems. Again, because systems consist of more than just your own software. Any of you building any systems that are not using third-party components or libraries? I know I'm blinded, but I'm guessing I see no hands. Anyways, that is just one thing. So actually, we should deliberately extend trust to those libraries. It's just an example. Another place is the input that we are getting into the system. Where does that input come from? That brings us back to all the attack vectors. Because what do we want to do in order to handle that input that is untrusted? What can you do? One thing is input validation. That was a good old thing, but having been doing that and putting that into the project where I'm still connected today, I also know that that is very much not complicable very much with usability. You set in a new input validation, a whitelist that you want some input to conform to, and then some legitimate customer enters something that we hadn't foreseen. So I have proposed a 5-layer decontamination airlock, you could say, from a sci-fi movie. And without going in too much details, it is like input validation on the encoding system. So for instance, if we can just agree we accept only UTF-8, then we are kind of mitigating what we call encoding confusion. Layer 2, sanitization. In UTF-8, as an example, there'll be 9 different kinds of apostrophes. All those different kinds of apostrophes might serve the same job in a malicious script, but if we cannot recognize them later when we need to know what kind of input is exactly that is accepted here, then we need to kind of prepare our later steps of validation to this. So that's why we clean up in the data. Step number 3, canonicization, also sometimes called C14N, C14 letters and N, or normalization. We are trying to take input that we might want to be able to recognize on a whitelist later and put it on normal form. So for instance, if somebody is trying to make a path traversal attack or directory reconnaissance attack, then we would, for instance, clean out //// when they are trying to reach, for instance, a password file on a Linux system. That is normalization. Step number 4 is one of two. Either it will be domain-driven security, or it will be input encoding to that third-party system that needs to take the input. So in case it is domain-driven security, when you are going to build domain objects in your domain model, you are actually in the domain where you know exactly what is necessary in order to populate a user object. So for instance, now you know that when I want to create a social security number, it is not necessary for me to have all these different kind of characters. So now we can validate against them. So that is what we would do there. Otherwise, the input encoding part is if data is going to go into the database or an LDAP authorization server or a cloud environment, then we would kind of validate against that or encode it in that system. So it's going to be interpreted as SQL sentences and not any injected command. Good. And step number 5 is output encoding. And that could be, or that is in order to protect the user. So for instance, if something we get out of the LLM is going to be shown in a browser, then we would make sure that, for instance, if it's only an HTML context, that JavaScript will not be able to execute. That is output encoding and the 5-layer decontamination alloc. Good. Another thing to remember is that input in the age of AI is a lot, because input becomes output, which becomes input when we are chaining AI agents and tools and everything. So we actually need to handle both parts. Anyways, being reluctant to trust is important. So don't let our butler do everything in our house. Good. Minimizing the attack surface. The oath is, I will always configure AI components to the bare minimum needed. No unnecessary features, dependencies, or access. So, for instance, imagine your system or a new LLM model, like a Swiss Army knives with all the blades extended, just waiting to cut yourself. So you need to turn in the blades that you do not need. All right? And at the same time, our butler, well, let's turn off the features that it is that he can go on the internet or communicate to the internet. Maybe he is also gullible and can easily be swayed into something that he was not purposed to do. The best thing, this is not directly AI related, you could say, but in relation to third-party dependencies, the big problem about the entrance of AI is that now we are going to pay for our past mistakes at a rate that we are not used to. Because an AI is many, many, many times faster, maybe 500 to 1,000 times faster than a nation-state hacker. Some of you might already have heard about the Mythos project. It's not released yet, but of course it will leak at some point. So the best thing you can do to handle third-party vulnerabilities is to minimize the attack surface. It is better than having a good patching schedule. How do you do that? Well, first of all, make sure that if you have some functionality you're using 3 different libraries for, decide on one that you can trust. Secondly, do not use multiple different versions of the same library. And third, turn off all the features that you don't need that account for everything you're connected to, where you are in control and your software yourself. That is prime examples of minimizing the attack surface. Number 4, compartmentalize. And the oath is, I will always sandbox my LLM as an untrusted prisoner. It holds my secrets, but its loyalty is for sale when the currency is prompt injection. Well, the thing is, prompt injection is not like now we are making a syntactic hack on some system anymore. Now the hack is in the meaning of words. It's a lot more difficult to guard against. So how do we do that? Again, it is gullible, meaning that it can easily be swayed into do something if it is tricked. You can call it social engineering on a statistical machine. That is actually what prompt injection is. At the same time, it's also OWASP risks number 1 on the top 10. And for those that might not know, OWASP is the Open Web, or worldwide you choose, application security project. They have also made a top 10 list for OWASP risks. I have it in the slides, but it's actually meant as a handout for you. And prompt injection is a stepping stone to so many other things, just like cross-site scripting used to be a stepping stone to so many other vulnerabilities in the past. Compartmentalizing. Do not let our butler get into the garage with the expensive cars. He's supposed to be in the house. And if he's not supposed to work at all times, then put him in a cupboard. From a more practical perspective, you need to figure out where your critical assets are in your system. So if an LLM actually has access to your confidential data or other secrets, which I, as a first off, would say that's not a good idea, but if you need, then at the same time, it definitely should not be connected to the internet. You need to compartmentalize. It has become so much more important these days than it used to be, even though it's one of the greatest architectural things you can do in relation to security. Things that are done very well up front, and if you get out later that it's bad, very expensive to fix. Compartmentalization, that survives. Number 5, least privilege. I will always assign the least possible privilege to an AI component, large language model or AI agent. It should never exceed the operator's privilege. Now again, what is our butler allowed to do in the house? Where should he be able to go? What kind of keys should he have access to? What about the safe? Probably do not give him access to the safe. You will have to clean that yourself. So, at the same time, operator's privilege, that leans towards a thing we called keep user-bounded autonomy, meaning that an AI agent should never have more privilege than the user that it is acting on behalf on. Then you might say, but what if a user is not actually using the agent directly, but it's simply just put into an autonomous chain of a lot of different actions? Then the rule is more over in the minimize the attack surface. It is better with multiple special purposed agents, like than having one agent that has a lot of different capabilities. Because if one is exploited, then it can do less damage to the rest of the system. So, principle of least privilege, still very important. Number 6, I will never tell secrets or pass personally identifiable information and confidential information to an AI that has access or can be accessed from the internet. That's just what I said in the previous slide. So, do not share your credit card details with our dear butler. That's not a good idea. The thing is, an LLM is not just like a normal database. When you add information down there, you know where it goes. It doesn't go anywhere else unless that you, with linear logic, programmed it. But with an LLM, data that you put into it also becomes part of the training data. And remember again, the way to hack an LLM is by semantics in words. So that just makes it a different case. And the best way it doesn't happen is by not sharing it. Otherwise, you are back to the compartmentalization principle. Human in the loop. I will never assign critical operations to an autonomous AI agent. Human authorization must always be required. Well, remember, now we are sitting in the cockpit of an experimental fighter jet with a co-pilot that is, in one time, a mathematical genius and a very helpful and eager intern. It's okay, it calculates the path of travel and maybe the fuel consumption and so, but do not wire his control board up to the launch of the missiles. You need to be part of that. And then you might say, well, doesn't this impede the entire purpose of using AI, that it should be so efficient all the time? Yes, that's correct. And we have a lot of different AI vendors that are competing in a race beyond what we have ever known. But this is kind of the speed limit in that race. We need to take part to some extent. There are a lot of different things that will back this up. There's also something called the AI dilemma, but that is not the talk of today. So yes. So what about our dear butler? Well, if he really needs to go online, you need to be in the loop there. And if he needs your credit card, you need to be in the loop. So do that. OWASP top 10 for LLM applications. This is not what the talk is about, but then again, it might show how do our principles actually work in the battlefield. Because these different OWASP top 10 risks are really what mostly goes wrong. That is what attracts the most vulnerabilities and security problems today. So for that reason, we are back to blinding you again. Sorry, now I can see you actually. Anyways, here we have the threat model from before. And is it 9 minutes I have left? How much will be late? Okay. Otherwise, I'm done in 4 minutes. But yeah. We have our principles down here in the left-hand corner. And the thing is, the first two principles are actually ubiquitous. They just fit everywhere where you are now going to see OWASP risks on this threat model diagram. The first one is prompt injection, as we already talked about. And then we have sensitive information disclosure, where it's more likely that we are leaking information. As I told you, for instance, every time we put something into an LLM, it becomes part of the training data. And if a cloud ML engineer actually works on that well, then he will be able to see some of that training data. That's why we have sensitive leakage down there. Supply chain, we already mentioned that in relation to minimizing the attack surface. Also being reluctant to trust, that's really important actually. Then we have data model poisoning. For instance, there's an LLM called the Poison LLM. There they changed everything in relation to the Eiffel Tower. So it ended up being located in Toronto, Canada. So everything you asked the LLM about, both routes and whatever, then it was to Toronto. So how do you figure such things out? Now you might know where the Eiffel Tower is, okay, but still it could be more subtle than that. But that happens down here. And how do we figure that out? Again, we can be reluctant to trust in that matter. Number 5, improper output handling. So what is it that we're showing to the user? That is, again, back to the 5-layer decontamination airlock. Excessive agency. That is 2 places, both here at the model itself and then down in the back end here where we might have some excessive agency with the agents working. And I can reveal to you already that all the principles account for this. They all will address that issue. Number 7, system prompt leakage. The thing is, system prompt is generally something that the integrators of a model at your workplace would put in. So that is right, like the prompt that should rule any user prompt made later. But it might also tell what are the rules for this LLM. So if that could leak somehow by a trickster that is social engineering our LLM, then it might leak that way. Number 8, vector embedding weaknesses. Again, vectors are mathematical vectors, both in the negative and the positive domain, and up to 3072 long. So it's kind of hard to figure out what is down there. So getting it poisoned to the vector database, of course, that's done by experts, is actually also a possibility. Misinformation and untrusted prompt sources. There I can get back to principle number 7, human in the loop. There's one thing I think is very important. So in addition to not letting it do critical operations, there are 2 other things that are important. First of all, training your users of the AI. And second, trying to fight over-reliance. The point is that when we are asking an LLM a question, and it looks in its vector database, it will gladly invent a statistical bridge between 2 unrelated facts or maybe 2 conflicting things that it's going to put back at you with very, very confident and authoritative communication. And we are just biologically wired to trust that thing. So people, again, are important. Number 10, unbounded consumption, also sometimes called denial of wallet. Here we are thinking about a risk where it is that we have an AI in a cloud environment and it might incur a lot of cost. So if we have the people sitting on the outside performing some operations that cost a lot of compute, it can actually cost a lot of money. We know that cloud providers are very expensive. But anyways, they fit the battlefield. Excessive agency, having all but rest. But this is as a handout. So, yes. I also made a talk on this top 10 at some point. And when you're looking at all the different kind of mitigations across the OWASP top 10, you have nearly 100. So I tried to assemble the 10 most effectful ones as I see it. And now, for the service for you, I have also attached the small icons attached to the principles that are presented here today. And you can see they actually fit everywhere in relation to these mostly valuable mitigations. So that is also for your handout. Good. There's no escaping reason, no denying purpose. We as humans are mathematical, the biggest security liability in systems. It is mathematically proven in numerous reports. So our dear butler eventually chose that to change all the locks on the house because apparently we were the ones tracking mud into it all the time. Function precedes choice. And you need to design the limits. Thank you.